the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 88, where today, we're just going to be talking about some quantum mechanics and statistics.
That is correct.
That is correct.
I'm actually currently taking quantum mechanics.
And
third
I'm
year
actually currently taking statistics. I think people are knowledgeable of this.
So
Mention it.
that's right. I know Ray has a couple of notes, but I don't have any notes. I'm going to be speaking off of the dome
Notes
today.
as in I'm looking at the stuff that, we went over in class just to succinctly organize some of the stuff. Cause I know sometimes, cause I'm taking multiple statistics classes. So they do overlap sometimes, but one of them is significantly more advanced. So I may go off track. So just keep me in check.
Yeah. So today I'm going to be speaking about things about quantum mechanics because I find my class right now to be really, really interesting. And there are just some things that I want to share, but just know that talking about quantum mechanics without a whiteboard or prior knowledge of quantum mechanics is pretty difficult to just understand. And so I'm going to be being very general and picking very specific examples for the stuff that I'm talking about. And so, yeah, we'll see how that goes. I think it'll be a really great topic to talk about.
No, I think quantum mechanics, we can definitely both dive into. And I think you mentioned this on the last episode when you kind of teased the fact that we're going to talk about this. But quantum mechanics is based in statistics. It's a statistical approach to the universe. So it's kind of cool. We're going to be talking about probability distributions a little bit here and there. Yeah. So we know where the normal comes up. So that'll be fun.
Yeah. So before we actually get into the podcast, we have a quick little news session really quickly. Downloads, where are they at? 314,000.
Ooh,
crazy.
Close to 500.
Spotify followers, we're at 18,300. Very close to 20,000. And on YouTube, we're at 2,000 and something.
2,030 subscribers.
So make sure to follow the YouTube channel and check out the videos and leave a comment. Because we read your comments. Just know, quick note, by the way, before anything, I just want to say that Ray and I, right now, are so busy. It's incredible.
Yeah, that's a good start. Yeah, we should definitely address that.
So we read every single comment. We don't answer every single comment. That's just half busy, half lazy. But we do read everything. So thank you so much to everybody for commenting.
But sometimes, if you look at the last episode, all of a sudden you'll see Math and Physics Podcast is now replying to comments. Because literally I just had 10, 15 minutes and I'm like, oh, okay. And I just started replying to, you know what I mean? So it's not like I read every single one of them, but sometimes we read every single one of them. It's just sometimes we don't have the time to reply, and we love some of your comments. Absolutely love them. I know the continue to subscribe. The comment was very funny. So continue to subscribe to the podcast, basically. And why would they want to comment on a podcast episode?
I have no clue.
Comment of the week. So every week we choose a comment of the week on each successive podcast episode. So this week we have Algo Kohlberg. Might be mispronouncing that, but they say, "Hi from Sweden. I've been listening to the podcast for a year now and I absolutely love it. A 16-year-old studying extra math and physics. You guys have given me invaluable intuition and inspiration. Keep up the good work." And then they say, P.S. Favorite episode, A Linear World.
That was a good episode.
That was a good episode.
Linear algebra?
The linear algebra episode.
I gotta say, linear algebra is definitely top 2 best math topics to study.
Best math, yeah.
Top
for
2.
Sure, 100%. Also, one thing I do wanted to brush over is the comment section for the World Scientific book giveaway. Just wanted to keep everyone updated. It is happening. It's just a little more communication on our part with World Scientific itself, but it will be happening. So don't worry about the people that commented. They're like, oh my God, when we're going to get the book? It's going to happen. It's just about
also for merch, by the way, It's a little bit harder than we thought it was going to be when we announced it.
Selling merch is not just, hey, do you want to buy merch? Okay, it's not as easy as that. You got to do a lot of setups. You got to set up a lot of things, which is not, I mean, it's not hard. It's just that we have to do it. And again, as you very well mentioned, we're a little bit busy.
We're very busy.
We're a little bit busy. So we just have a lot of schoolwork, a lot of things just always coming up. So we will do this in the right time, but it will be coming soon. So if you guys like, the merchandise that we kind of showed, never really said that whole word. The merch that we showed on the IG and stuff like that, keep it up because it will. Keep it up because it will be coming. It will be coming soon.
Yes. All right. Is that everything?
I think that's everything.
I think that's it. All right. Do you want to start or should I go first?
I mean,
should we alternate or I don't know.
We can alternate.
Okay, let's alternate. I'll start. Here we go.
We can start with some quantum mechanics.
Quantum mechanics. Why do I love quantum mechanics so much? Maybe like a 30-second intro if you've never heard of quantum mechanics. Basically, quantum mechanics is a very, very good description of what happens when you zoom in very far into matter. Basically, like the microscopic world is very different, surprisingly enough, because this isn't obvious whatsoever. If you study the motion of a ball when you throw a ball, you say there are certain rules that govern that motion. And then you would assume, like, if I make the size of the ball half the size, then I can still apply the same rules to that ball. But then when I divide it by 2 again, and then I keep dividing it by 2 until it gets to the size of a proton.
Oh, what happens
surprisingly enough, we found that it doesn't follow the same rules. It just doesn't. And this, people, I don't know if people say this, but people say like, oh, quantum mechanics it's just like a theory. It's, it's like some weird like physics, a lot of symbols, but it's pretty mysterious and stuff, but it's actually what happens. And in fact, it's our best description. Now, here's the thing. We will never actually know, or at least this is a debate, right? Whether we'll actually be able to describe the universe completely, which I don't think so. But what we can do, well, Newton comes around and he describes motion.
So you're like stuck with a probability. You're good with the probability definition of the universe.
No, I think there will be a better description in the future. Yeah. But then there will be a better one. And then every time we find a better one.
That's the whole purpose of science, right? Yeah. Like always keep progressing in whatever.
Exactly. But the thing about quantum mechanics is that it's really good. But it's also really spooky and very kind of like why we have no idea why. We just plug things into the equations and we're like, wait, statistically, like I can prove this using math that this shouldn't happen. And oh wait, it literally explains something in the physical world. And we're like, oh, that's pretty surprising. Like, why does it work that way? We don't know why it works that way, but we know that we have a good explanation for it.
Well, we do have multiple. We always talk about the many worlds interpretation, but like as of right now, the Copenhagen interpretation, like the probabilistic view of the world, is basically where we're at.
Yeah.
Right. Because I think that also goes very well with the math and all. So it just works.
So here's a very that was a very brief intro. Now let's get into some quantum mechanics. Think about the classical world. How do you describe things that are measurable, right? What is measurable? You can measure position of an object. You can measure the momentum of the object. You can also measure like the energy, the total energy of an object. There are lots of things that are measurable about an object. In quantum mechanics, we call these things observables. And I love the word observables because it's all in the name, right? It's something that you can observe. Now, the surprising thing about quantum mechanics is that mathematically, you can show that some of observables don't commute. What does that mean? Commutativity, I think that's how you say commutativity, something like that. In mathematics, it means that, if you do 1 times 2, it's the same thing as 2 times 1. It means you can just
1 and 2.
It means that you can just switch them around. And if we put this in the context of like measuring something, that's like if I decide to measure the position of a ball and I decide to measure the momentum of a ball, I can do it in either order and it would give me the same answer, right?
If they commute. Is the
right, well,
commutation.
Classically, everything commutes,
of course,
right?
Of course.
Or maybe I don't know enough about classical mechanics.
I mean like a simple example for so give me something that doesn't commute. Well, matrices.
Exactly.
I always love giving this example.
No, that's
like AB doesn't necessarily equal BA. So what that basically means is, like, if you think of matrices as like transformations, which is like a really sophisticated linear algebra, like algebraic way to think about them, you're basically saying applying the transformation A on matrix B is not the same as applying transformation B on matrix A.
And this is
which,
why,
if you say it like that, it's like,
it kind of makes sense.
It kind of makes sense. But AB doesn't equal BA. You're like, what? Why not? Right?
And so, what was I just about to... Oh, yeah. I was just about to say that this is why linear algebra is so important in quantum mechanics, is because it literally describes the fact that matrix multiplication is not, in general, commutable, which means that, BA is not the same as AB, is exactly why we decide to describe mathematically, we describe observables with matrices. Because all of a sudden, in the quantum world, when you want to measure the position of something, it alters the state of the thing you're measuring. And when you measure the momentum, you alter it in a different way, which means that if you measure the position first, you have no idea about the momentum. And if you measure the momentum first, you have no idea about the position. And so when you calculate something called the commutator is basically a measure of how uncommutable they are.
How about you talk a little bit about like why? Because I think that could be an interesting question. Like why, when you measure position, you just have no idea about momentum.
I mean, intuitively, there is a picture I can paint, but mathematically, you just have to do the math. But
yeah, mathematically is a little different, but I think like you can still explain like, the whole, the wave. You know what I mean, right?
Yeah, I mean, we have explained this before, but I can also give you like an intuitive picture as to why we can't measure the position and the momentum at the same time. And that all comes down to the fact that when you zoom into matter a lot, things like the very act, and I remember being so confused about this. Like, why is the fact that I observe something changing the properties of the thing itself? And here's why. Because when you zoom in so far, the size of photons, well, I'm not going to talk about the size of photons, but like a photon itself and a particle like interact on the same like energy type level. You know what I mean? That's like if I send a photon at an electron, that electron can absorb the energy from the photon and, become more excited. Or it can emit a photon and become less excited if it's in a bound state of an atom, whatever. The thing is that, we've observed this through like the Compton effect, for example. And the Compton effect is that if you bounce a photon off of a particle, or I think it's an electron or something, if you bounce a photon off of an electron, based on the angle of deflection, it will tell you how much momentum has been transferred. And so you can actually see that you send in a photon that has some wavelength, and then you bounce it off of something, then you measure the wavelength again of that photon, and you see that the wavelength has elongated. Why? Because longer wavelengths of light have less energy, which means that it transferred energy to the thing that it bounced off of. Boom. Now, here's where it gets interesting. What if I say I want to measure the position of a particle? What does that really mean? That means that, well, I need some like visual representation or some like numerical representation of that position in some coordinate system. How do you measure the position? Well, you need some sort of thing to go out, see where it is, and then come back into your detector and be like, oh yeah, that's where it is, right? That's the only way you can really make a measurement. Like you can't send out information and then it never come back to you, because then you'll just you'll have no way of recording something. So you want a signal to go out and to come back and then to confirm, yes, that's where it is. And so in this case, when you look at something, that's because photons are bouncing off of that thing and going into your eyes. But when I look at Rayhan right now, photons are coming off of his face into my eyes, and I can see where he is because of that. But he's so big that the energy that a photon transfers to his face as it bounces off is so negligible that, you know what, even though a photon has bounced off of Rayhan, he's still here. He hasn't gone out because of the sheer force of the photon. But remember how I said that when you zoom in very, very far.
So my individual electrons probably.
Exactly.
Some electrons probably went haywire.
Exactly. What happens is that when you send photons at electrons, they literally bounce off of the electrons and the electrons go somewhere, right? Now, if I go to measure the position of a very small particle, I am bouncing photons off of that particle, and those photons are coming back into my detector and saying, yes, this particle is in fact here. But from the time that the photons bounced off of the particle to the time that they were detected and I can say, yes, here is the particle. Remember, those photons transferred momentum to the particle, and that particle bounced off of the photons at some angle. And by the time that I can confirm the position, I have no idea where that particle is because it just bounced and it's somewhere else now. And so that's kind of an intuitive idea as to why if I measure the position, I don't know the momentum. And if I go to measure the momentum, I have no idea about the position because that's just how it works when you zoom in really far.
And an interesting thing that comes out of that is, I love talking about this, the observer effect. I don't think we spoke about it on the podcast before.
I don't know.
Anyways, the observer effect is like this common, very, very, very common. Okay, I think I'm getting deja vu right now. I might have mentioned this before. But anyways, we're talking about quantum mechanics, and you were talking about observations. So I just feel like it's a cool thing to mention. The observer effect is like a very common misconception in quantum mechanics. And we were talking about this the other day, I remember. And it's basically exactly what you said. When you're measuring something, you're usually altering the state of said something. So what happens in the state after you've measured it will change after your measurement. And in quantum mechanics, like a common thing is people don't really realize, well, when is the measurement done and how does it affect the state? Common, simple example, the double slit experiment. When everyone says, you look at it, and it breaks. Like, that's not really why, though. Like, the reason it's breaking is because when you look at it, as you very well rightfully just said, what's happening is a photon is bouncing off of the electron and coming into our eyes. Or I guess we're not doing it with electrons, but whatever particle we end up doing it with, whatever we're observing, we're going to be changing its state. So what that's basically doing is that's pinpointing the electron. Oh, it's right there. Right? Let's say we have an electron and let's say we're observing it. Let's just say with our eyes. Obviously, very, very simple analogy here. What's happening is the photon is bouncing off the electron coming into our eyes. And everyone's like, oh, yeah, this just broke quantum mechanics, right? Like there was a big thing and big misunderstanding of, if you observe something that breaks quantum mechanics. But no, that doesn't break anything. That actually follows the laws. It's just about what's happening when you say you're breaking quantum mechanics. And this is the observer effect. That when you observe something, you basically change its state. And therefore, any measurement made with said state after observation is completely futile. Right? Super powerful.
I wanted to talk about the Schrodinger equation.
Oh, that's a crazy one.
Because the Schrodinger equation is very, very cool. So, what is the Schrodinger equation really saying? It's essentially an eigenvalue equation, which just means that if you have some state, if you measure the kinetic energy of it plus the potential energy involved, you will get the total energy. And so that's all the Schrodinger equation is saying. It's saying that you have the first term is minus h bar squared over 2m times the second, or I guess the Laplacian of the thing. The Laplacian is just, you take two spatial derivatives in each direction. And it turns out that, I'm not going to explain why, but it turns out that the second derivative, let's just talk about one-dimensional wave functions here. The second derivative of the wave function is related to the kinetic energy. Then, for the potential energy, you just multiply the potential times the actual function. And that's equal to, I think it's like I h bar times the time derivative of the thing. Now, what does all this really mean? On the left side, you have something called the Hamiltonian. And what the Hamiltonian does is it just measures the total energy involved. And on the right side, you have just the energy of the thing times the thing itself. So it's if you break it down, it's really simple, but it's still hard to use if you're taking quantum mechanics right now. It's still kind of, they pose you a problem and you just have to play around with the mathematics and solve it. And I want to talk about one of the problems I did this year, but it might go on for too long, so I'm just going to get to the point of what I'm trying to say.
So far we're just talking about quantum mechanics.
Yeah, I wanted to talk about the mathematical description of a plane wave and why it is how it is. And this is very interesting. So a free particle, you can imagine a free particle as just a ball rolling on a floor that is just perfectly level. And this analogy is used because there is no like gravitational potential change in this case. If you were to roll the ball up a ramp, then the kinetic energy would give way to the potential energy as it goes up the ramp, and then the ball would be able to stop and then roll back down. But if there's no ramp, the floor is just, we're assuming no friction, the floor is just flat, and you send a ball at a specific momentum, it will have that momentum forever. And so one of the defining qualities of this ball, and now think of the ball as a particle. So one of the defining qualities of this particle is that we know its kinetic energy because we say, or I guess we can observe the momentum to have one single value. And if we measure it now, it'll have the same value later because there's nothing that can change that value. There's no sort of potential that'll be able to take away from that. And so, why is it that we have no idea about the position? Here's why. So if you use the Schrodinger equation, you look at the right side of the equation where there's a time derivative. The energy term in here is just the kinetic energy. And so when you take a time derivative of this state, what you're going to get, or you multiply it by IH bar, whatever. Essentially, when you take the time derivative, you should have the energy times the function itself. Now, you don't have to understand, if you're listening to this right now, you don't have to understand like half of the things I'm saying. Just understand the key points. And here's a key point. The key point is that when solving the Schrodinger equation, half the time you're guessing because that's what we had to do in the beginning, right? Now we know, a very good way to describe a free particle. And it uses like exponentials and like imaginary exponentials, meaning that it's like e to the I, in this case, IPX. Sorry, not IPX. I'm not even going to bother saying the math.
Yeah, you don't have to talk any about the math. Just like talk about the concepts.
Yeah. So when you take the time derivative of one of these exponentials, you will have the energy term come down from the exponential because that's how you take derivatives, and chain rule, and it comes down and you have this momentum value, and because that's the only thing contributing to the energy, and we know the energy of the particle because we gave it a momentum. You can guess this exponential as a solution, and as long as it works, right? As long as it works in the Schrodinger equation, then it is a valid way to write down the state.
Believe it or not, like a big part about like solving differential equations and equations is just guessing a solution. Mm-hmm. Like I like straight up remember like my professor so recently just being like absolutely cracked up the whole class when he's like, okay, so we're gonna guess this. And it just worked.
Yeah.
And I'm just like, okay, because you knew it, but like, how are we supposed to, you know what I mean? Like, but there's a big part where obviously when you're told a correct guess, you're like, oh, okay. But like actually figuring out the guess is pretty hard. But I'm assuming obviously it follows a particular model where e to the ix is a valid guess. Like there are certain criteria and stuff like that for guessing and stuff. But guessing is basically a big part of it.
It's a big part. And
it's a big part of it.
I remember in first year, we were doing this differential equation, which we had no idea what differential equations were.
Yes,
and the prof was just like, you guess this solution and then it works. And we're like, what is going on?
And he told us, he told us the guess. And I'm like, yes, I know this works.
How can we just guess?
How do we guess it? Like what?
The more you do math, the more you realize like,
that's basically
that is a very good guess.
It's just a more intuitive guess as you get better.
Exactly.
At what you do. Right.
So back to the free particle. Now remember, when talking about observables, I want to observe the momentum. I want to observe the position. These are described by like infinite dimensional matrices. And the reason why like this is so weird, it's like, why infinite dimensional matrix? What does that even mean? It just means that when you write down your wave function in a specific basis, everything about quantum mechanics is essentially applying what you know about vectors and linear algebra to these states. And so if you imagine a vector, just a regular vector, and you have like, let's say the standard basis, so it has coordinates x, y, z. That's one way to represent your vector, right? It's a valid way. You say, I set up this standard, quote unquote, standard coordinate system. And if you follow the coordinates, you go this much in the x direction, this much in the y, and this much in the z. And that is my vector. But if I want to change how I represent my vector, then what do? Well, you can change your basis. And then depending on which basis you're in, you get a different list of numbers that describe your vector. And so the exact same thing is happening in quantum mechanics with states. You can think about states as vectors. And you can look at this vector as in the position representation or in the momentum representation. They're just two different representations, equally valid and equally describing the exact same thing. Yeah. And remember how I was talking about lists of numbers? Well, the reason why a wave function is like an infinite dimensional vector and these operators that are observing properties about the object that we're trying to describe are infinite dimensional matrices is because in our case, we are trying to describe something that has infinite possible, infinite like pieces of information that you need to describe it. For example, we talked about the wave function being this probability amplitude. And basically what you're asking when you say, I want to know the representation of this state in the position representation, you're basically asking, what is the probability amplitude at this position? What is the probability amplitude at this position? And you're just listing out all of the possible probability amplitudes. Well, guess what? Position is a continuous spectrum. And so if you want to describe your state in the position representation, you need to be able to tell me the probability amplitude to find your thing at this position for every single position. And that's why your vector is infinite dimensional, because there's just an infinite amount of different positions that you can find the amplitude for. And then when operating on it, you're basically just doing matrix multiplication. And so that's one way to think about why these operators are infinite dimensional matrices. But not every single operator is infinite dimensional. And I want to get to an example. And I know we're getting low on time.
Yeah, we're basically just talking about quantum mechanics so far.
I wanted to talk about spin really quickly. So here's what we'll do. I think, I'll let you think about what I said about all of these representations.
Yeah, while we're talking about statistics, and then we can get back to some spin. We can see.
Really later?
We can see what the time is saying.
Okay.
We can see what the time is saying.
Well, that's a shame. Go ahead.
Well, that's a shame. But
if you want to know more, though, about quantum mechanics, what can you do? You can go to university. Sure. That's valid. Or you can go to brilliant.org and learn about quantum mechanics today, right this second. They have these interactive courses. When's the last time that you went to class and you're like, I absolutely loved what my professor just told me. Maybe a couple of times a year. Can you say that every single day?
I don't think so.
Guess what? Brilliant offers interactive courses. They say, here's the material. Here are some beautiful, figures to help you understand. And also, here are exercises that are directly related to helping you understand the material. And specifically related to this episode, they have courses on quantum mechanics. They have courses in statistics and probability. So if you want to learn more about that, make sure to head over to brilliant.org/MPP or click the link in the description.
Yeah, you can click the link in the description below for an added bonus there. For the first 200 people that click that link in the description below, they will get an easy 20% off their premium subscription for Brilliant. So check out link in the description below or brilliant.org/MPP. So a lot of quantum mechanics was being spoken about there, which is really cool.
Not enough.
No, of course, there's never enough quantum mechanics ever being spoken. But talking about observations, let's bring it on to the classical world. Let's bring it back to the real world, shall we?
Go ahead.
When you're actually observing protons and photons and whatever, like, you know what I mean? Like, you're not really gathering. You're basically getting things in a detector. You have all this data on a computer, and you're trying to analyze it, and that's super cool, right? But what about getting data in the real world?
This is the real world.
But I'm saying real world data.
Wow.
Statistics.
I would argue
Anyways,
that.
that was like an introduction, like a really weird introduction to statistics. But either way, statistics, not that I really need to introduce it, but is a way of analyzing real life data, or data in general, I should say. Statistics is literally widely used in almost every single field. It's widely used in quantum mechanics, right? Everything is based off of statistical distributions. Your probability distribution, fundamental ideas with a probability distribution is applied into quantum mechanics, and it's basically applied everywhere, right? So I wanted to just talk about two major things today. That's why I was just looking at what I wanted to talk about. I wanted to talk about fitting data. So when you're actually taking data in the real world, what do you do with it? How do you analyze data? I think that's a pretty common question from a statistician, or at least someone that wants to become a statistician.
Statistician?
Yeah, that's what it's called.
Okay.
Yeah, you know, like physicist, statistician.
Statistician.
No, statistician.
I don't know.
Statistician?
I don't know.
Come on, bro. What is that? Anyways, one thing I wanted to talk about was, so the basic idea of analyzing data. So usually when you have any piece of data set, if you have a data set, if you have some information, there's something that you want to analyze about it, right? There's a particular variable that you're interested in. For example, I can give the example that I'm actually doing for my final project. This is a really cool project. So the data set that I have is the data of the price of the S&P 500, the inflationary data from that same point. So every time that the price of the S&P 500 was taken, so is the rest of the data points. And I think it's inflationary data, it's earnings data, and it's a bunch of other variables. My interest in this situation is to study the price of the S&P 500. How did these variables influence the S&P 500, right? And that's basically statistics. Basically the most fundamental idea in statistics is how do you analyze data, right? And data analysis is done commonly simply by, first you want to identify what you're interested in. And this variable is called the response variable. So that's the actual response that you're interested in. And everything else is called independent variables, predictor variables, anything like that. They are commonly known as predictors, though. The reason it's called predictors is basically because what you're doing is you are putting a bunch of them together, and together they are predicting this final variable, right? So your goal in a big chunk of this is basically to correctly predict this final model. So in this particular example that I've been giving, I want to find the price of the S&P 500 and what actually influences that. That means as the S&P 500 increases in price or decreases in price, what happens to the inflation in the area? Because that's another variable that I have. as the S&P 500 increases in price, what happens to the earnings of the said companies in the S&P 500?
But what about like looking at it the other way?
Tell me.
Like what happens when inflation goes up? How does the S&P change?
Yeah, so
like,
those those are all.
You said the other way though. You
Okay,
said what happens
so
if the S&P changes?
Oh, that's what you mean.
Then
So in this case, remember, one of the first things that you want to do when you have a data set is identify your response variable. What are you interested in? In this case, I mentioned I'm interested in the price
so
of the
you
S&P
can
500.
put anything as the response.
You can put anything as the response variable.
So everything causes everything essentially. You know?
In this particular situation, let's say I also have another variable, number of squirrels, right? And every time the S&P 500 data was taken, the number of squirrels were also taken. Now, it just so happens that the S&P 500 is increasing and so is the number of squirrels. Does that mean they're correlated?
Maybe.
No, what I'm saying is there's random correlation, right?
Yeah.
So what I'm trying to say is not every predictor is related to the response.
How can you tell which one is...
So that is simply via intuition and...
Oh.
Yeah, I know. It's nothing serious. That's simply via... Like, if you're actually looking at random variables with respect to a response, there are tests that I actually want to talk about today. There are tests that can tell you whether this predictor explains a good amount of variation in the response. So basically what that means is when you have values in the response variable, if I change this predictor, if I take it out, if I add it in, is it changing it significantly? Is basically in a very, very brief way of testing these things. So I can do the squirrel comparison, and I mean, chances are it's not going to be able to explain a lot of variation, and then I'll be able to formally remove it. There are tests, but most of the time it is simply intuition. You're like, what the hell does squirrel data have to do with the price of the S&P 500, right? So a big thing about statistics, and I loved to learn this while my professor was talking about it, and she's like, this is where it gets this is where I'm pretty sad too. You can give the same data set to 10 different researchers and they will come with 10 different answers. Like, what the hell is the point of it? You
Exactly.
know?
Why would you ever do that?
Point of it being, it's all in how you interpret the data. That is why when you're doing like your experiment problem sets, and anytime you take data and it doesn't fit perfectly, it's okay. It's okay because there are always random variations. There are always added things that sometimes might not be factored into your data that you have, but you just have to figure out how everything is affecting each other, right? So that's a big part of basically what you're doing. And what I'm basically describing here is a model for linear regression. So in this case, most variables, I shouldn't say all variables, are linearly related to each other. Now, when I'm saying that, it's a little interesting when I say the word linearly related in terms of linear regression, because it's not actually the predictors that are linear. Instead, it is the coefficients on the predictors that are linear. And the powerful thing with this is that when there's an assumption of linear regression, there are a couple assumptions that basically a data set has to follow. And if those assumptions are satisfied, you're basically golden. You can do like a bunch of tests. You can like fix your data and you can basically make it look a little bit better. What does that mean? Fix your data? What do you mean fix your data? Let me explain that because I think that's important. Now, a common thing in most data we think is that data is mainly normally distributed, right? Now, that's actually one of the assumptions for a linear regression model, that the data is normally distributed. However, it's not always the case. So you think that intuitively things should be distributed normally.
I mean, intuitively, I would assume that not everything is normally
Most things aren't. So the thing is...
Wait, most things?
Most things as in when you're taking, especially when you're taking the number of data observations that you take, significantly impact it. So if you're taking like 30 to 50 observations, like it's not a very high number of observations, chances are your model is most likely not likely normal, unless the data itself is normal, right? And that's also based in a fundamental theorem that we can talk about. But basically, normality is like a very important condition for a lot of assumptions to hold. And when these assumptions again hold, you can basically then apply your linear model. And the reason this is cool is because of something known, and I kind of want to talk about this, the least squares estimator. This is why the linear model is really cool. Because basically what it's doing is you're taking your observed data or your response variable, and you're taking a linear combination of all the predictors. So let's say you have your response variable y, and your predictors are x1, x2, x3. What you're doing is you're saying y equals beta naught, which is like your intercept, your y-intercept, and beta 1 x1 plus beta 2 x2, beta 3 x3. And those are your coefficients. Now, here's where the linear model comes in. Your whole analysis comes from basically getting these predictors to be least biased as possible. Because in all cases, if you have non-normality, if any of the assumptions are broken, then basically what you have is you can still use the model. Like you can still fit a straight line to curve data. You can still fit the model, but your coefficients won't be biased. Will be biased. They won't be unbiased. And that's the problem. So when these assumptions hold, you can actually just tweak your data. You can sometimes square it. You can actually just apply transformations on the data. And you can actually notice that, hey, now it all of a sudden looks normal. When a few of these assumptions hold, you can now apply this linear regression model. And when you find these coefficients, you are satisfied with the fact that these coefficients are completely unbiased.
But then, hold on. If you apply transformations to your data, right? Do you have to reverse the transformation?
No,
after?
so then you're simply, okay, so for example, let's say y was not normal, and then I squared it, and now it's fine, right? That actually has happened. You actually can't do that. It's pretty crazy. So these are called power transformations. I don't want to get too much into that, but you can transform variables, and then now all of a sudden they actually satisfy assumptions. So when you square it, so usually let's say your coefficient on x1 is 2. That means as x1 increases by 1 unit, your response variable is increasing by 2 units. Basic y equals mx plus b.
Yep.
Now, when you have multiple predictors, you're saying as x1 increases by 1 unit and everything else stays the same, this increases by 2 units.
Partial derivatives,
right? It's all basically just singling one predictor. So if you now square it, for example, you're simply saying 1 unit goes up by root 2 units instead of 2. You know what I mean? Because the power transformation, and sometimes even your x variable can be transformed. Then it's a little more complicated, right? But if let's say only your y variable is transformed, right? Then in that situation, they'll simply be related by whatever the coefficient was, and then you're just applying
but then
y.
Square rooted. So you have to reverse the transformation.
That's what I said, root 2.
I know, but that's what I meant by reverse the transformation.
Of course, you have to reverse it when you're actually analyzing the data. Of course, when you're actually making the analysis step, then you actually do have to reverse it. But the whole beauty is that you can apply these transformations to variables, and all of a sudden you can now apply this model that makes the variables look linear. And not only, I shouldn't say makes it look, because then it's like, oh, you're changing the data. No. You're not changing anything fundamentally. You're just transforming them. And again, the relationship holds. It's just that when you transform them, you can apply linear regression, and then you can analyze.
But hold on.
But without that, you can't analyze. The analysis step is broken.
Okay, wait, never mind. I answered my own question.
What was the question?
I mean, I was just thinking about if you have your data that's not normally distributed, and then you square it.
Square is just an example of a transformation. It can be anything.
I know, but if you square it, then if it goes up by 1 unit, it would be different than if it goes up by 2 units because it's squared. So it wouldn't, even if you just root 2 times the x1, for example, wouldn't it be different for how many units it goes up by? No,
so as long as x is not transformed, right? X is, you're saying you're moving by x units. Basically, what your prediction is saying is, as you're in the case of y equals beta 1 x1 blah, 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 blah.
Oh, then you just transform the coefficient.
Exactly. So exactly, you're just moving with the coefficient. So you're saying as you move x1 units, your y or 1 x1 unit, if it's power transformed, you're just going to square root or whatever, that many x1 units, you get these many y units. is basically what you're saying. And that is basically analyzing data. That's basically the ABCs of analyzing data. Because if let's say, for example, I'm interested in finding out how does inflation increase with the price in the S&P 500, I apply these transformations, and then I'm like, oh, that's interesting. And all of this works with the least squares estimator, which I kind of brought up like a few minutes ago. And the least squares estimator is like this super powerful thing, which basically is just like, hey, all your observed data so there's going to be some line of best fit that's going to be fitting your data. And all your observed data either lies above or below this line of best fit. Your goal to find the coefficients of this line of best fit is to minimize the average distance between the observed data and the line of best fit. And that's basically the kind of how you define your line of best fit. And interestingly enough, this is done via a chi-squared distribution, right? By minimizing chi-squared. Or at least in some programs, like that's a very sophisticated way to model a distribution by minimizing chi-squared. And chi-squared, interestingly enough, it's just another probability distribution. I mean, all of these distributions are just, all these variables that we test, like the t-test, your probability tests and your chi-squared tests, all of them come from distributions. A chi-squared distribution is just a sum of squared normals. And if you actually look at the chi-squared statistic, like what you measure to see how good or badly your data fits the model, that if you expand it is literally a sum of normally distributed variables. So you understand that your chi-squared statistics is basically minimizing, or your chi-squared distribution, but you're seeing at what point is it minimum, right? And using that analogy or using that idea, you're basically finding your coefficients for any model.
But hold on, if your chi-square is a distribution, are you talking about when the mean is a minimum, or like the median of it is?
So what you're actually doing, what you're actually doing when you're doing this is you're performing a hypothesis test on chi-squared. And so what you're usually doing is you're hypothesizing that chi-squared will be minimum. So you're looking at, okay, what are the values if chi-squared, like reduced chi-squared is 1? So your goal for reduced chi-squared is 1. So if your reduced chi-squared is relatively close to 1, it will basically spit out a positive test, and therefore that chi-squared is valuable. And then any numbers from the chi-squared, which will basically contain your betas, you can then minimize them using that, right? So it's also something that I just kind of skimmed over, like a hypothesis test. This is the most fundamental idea in statistics, a hypothesis test. It's basically testing out a hypothesis. Very simple. And a hypothesis can be as simple as, I walked 5 minutes today. That's my hypothesis. Is it correct? Am I accepting it? Or, okay, technically I cannot accept the hypothesis. But the way that the hypothesis test works, and this is where it gets really cool, is basically you make a statement about a given data set, about a given variable, sorry. So I say, I walked 10 minutes today, for example, right? So my variable is me walking, and I say that the mean or the maximum or the total amount of walking that I did equals the 10 minutes. So what I do is I perform a hypothesis test on this variable. Now, how the hell do I do that, right? How the hell do I do that? So hypothesis tests are actually based on a very fundamental notion of standardization, standardizing variables. So anything, any distribution, any data with a finite mean and a finite variance, so a finite average and a finite standard deviation. Now, if you haven't heard of these terms before, you might be thinking, when can you have an infinite average? Believe me, you can. I'm not, maybe not the best time to talk about it, but there are distributions such as the Akashi distribution, for example, that has an infinite mean. So
wait, hold on. Intuitively, I would, because I don't know about any of these distributions that have infinite mean. Would it be normalizable or no?
No.
That's what I was thinking. That's what I was thinking.
You can't normalize it. You can't standardize anything that doesn't have an infinite mean, because the actual formula for standardization requires subtracting the mean from the variable.
But how? What can you apply to a Cauchy distribution to?
Okay, this is a good question. I don't know off the top of my head, but I know there are answers. There are answers because because my professor was talking about the Akashi distribution, and someone was like, when are you ever going to need this? And he said something, and there are answers. I'm currently unaware of this, but I do know that their answers do exist. You do sometimes need because it's like a step function or like something like that. That's why it just keeps on increasing. That's why there's no actual mean. But the reason and where you actually use it, I'm currently unaware of, but I know it exists.
So the function increases as you go higher?
Yeah, which is why it's an infinite mean, which is it's like some weird function like that just never stops, which is how that can happen. Right. If otherwise, if it ever increased and decreased, if it ever did anything like that, it would have a standardizable mean, right?
Not necessarily.
I mean, most cases, it might have at least a finite mean.
Like if it's sinusoidal, then...
Okay, that's actually a good example. But okay, that's actually a very good example, yeah. I guess distributions aren't really...
I don't know how that would be possible, but
like,
I mean...
I guess.
What if
because again, it does have to be a probability distribution. So it doesn't like add up to 1 and stuff like that. So
it is normalizable.
What?
Because if you take the integral, it has to add up to 1.
No, like all probability distributions need to integrate to 1.
Exactly.
So like remember like the step integral that we used to do? Like we can still integrate that, right? But it doesn't mean it has a finite, it doesn't change the fact about the finite mean or a finite variance. Because the only way to standardize a variable is with finite mean and variance. And that is based off of the central limit
But wait,
theorem.
that doesn't make sense though.
Why does it not make sense?
Because how is the mean infinite if you can integrate it from minus infinity to infinity?
Again, I'm not too well versed with the Akashi distribution whatsoever.
Well,
I simply know that it is an example that breaks.
I'm talking about any distribution.
If it has an infinite
mean,
okay,
but it's normalizable because it has to have a finite.
No, but that doesn't mean you can convert it to a normal distribution.
That's not what I mean. That's not what I mean by normalizable.
But that's what I'm saying.
No, okay. What I mean
I'm standardizing it.
Okay,
I'm saying standardizable.
What I mean by normalizable is that you can it has a finite integral over
well, that's
all
simply
space.
a fundamental property of a probability distribution.
So how is it possible that the mean is infinite if you can integrate it all the way across?
No, because it's definitely. I mean, I know for a fact that the mean is infinite. I also know it's a probability distribution, so it has to satisfy probability laws. Quite unaware of that question. That's a good question. Again, answer definitely exists. I'm just currently unaware of it. That's an interesting question.
Yeah,
definitely going to give some thought to that.
Yeah.
But continuing to the CLT, because I was just bringing that up. That's basically the theorem that governs everything I was just talking about, right? So, if a variable has a finite mean and a finite variance, you can basically what the central limit theorem says, as the number of observations increases to infinity, the variable approaches a standard normal distribution. Now, it's not the variable, it's actually like a transformation of the variable, but a transformation of the variable, a linear transformation of the variable, leads to a standard normal distribution. Now, you might be like, why does this matter? This is so stupid. This is why it matters. Because when you have a standard normal distribution, you can get probabilities very easily, first of all. And because they're all like z values, like your z-score values. Mm-hmm. So number one, you can get probabilities very easily. And number two, it's symmetric. Ooh. So if you make a test or if you hypothesize on something that happens on the right, it also happens on the left. Now here is basically what you do in hypothesis testing, or mainly like standard hypothesis testing. What you're doing is you're first transforming your variable to a standard normal, which is basically just subtracting some things and dividing some things. Nothing too complicated. But in my case, I said I want my mean, my total walk time today was 10 minutes, right? So I performed some transformations on my variables. And I'm basically like, what is the probability, right, that this value, what do I call it? I would say the standardized variable now. Let's call it the standardized variable. So what's the probability that the standardized variable is less than some cutoff value? What is a cutoff value? This is where the normal distribution comes into play. So usually, this is known as the p-value. So usually, the p-value is at 5%, so 0.05. So what you're basically testing is, or what you're hypothesizing, is what is the probability that this standard normal or this standardized variable, where it is on the graph of the normal distribution, what are the chances that it just happened randomly versus it actually happened? So basically you're saying, is it at the end of the tail, like really end of the tail, or is it somewhere in the middle? You know what I mean? Because if it's really at the end of the tail, it's basically not happening. It may have just happened because of random chance. If it's basically the other end of the tail, same thing. But if it's somewhere in the middle, that means like, okay, this definitely happened due to an actual reason.
Isn't 5% like within 2 standard deviations of the middle, you know? 5% on each side?
Oh, yes. Because approximately.
Or a little bit less. A little bit less.
Because one standard deviation is 65.
Yeah, and then 95.
And 2 and 95 or 97 or something like that.
It's 95.
Is it 95
exactly? I think 3 is like 99.
Is it exactly like that?
Like 95 points.
Okay, then maybe. Okay, yeah. So but remember, this is
I know it's on both sides.
Exactly. So it's 5% on both sides.
I remember we did this.
But I'm saying it's 5% on both sides because remember the value could take on either side.
Yeah.
So anyways, all this to come basically to the idea of hypothesis testing is that when you standardize this variable, you are now able to test whether this particular observation, this mean or whatever, happened just by chance or it was actually a reoccurring event. And this is your hypothesis test, right? So in the case that I said walking equals 10.
You would need data on your previous walks,
no, of course.
Right?
No, I would need data.
Okay.
But I'm saying with this, no, I would need the mean and I would need
the
my standard deviation. So obviously I would need a lot of data because I'm getting the mean. But this is also the thing. As your number of observations are low, the results are a little less and less accurate. Even though they can always still be standardized, it's just that with more observations, you always get more accurate data.
And this is what I don't like about statistics, because I was going to ask you, like, when you test your hypothesis, there's probably, like, you calculate, like, because you have some data set on how long you walked in a day, and then you calculate the mean, but that's just an estimate for the mean. So then there'd be an uncertainty in your mean and like an uncertainty in your standard deviation, which means there'd be an uncertainty in whether your hypothesis is right or not.
So there's a standard error, which is your standard error variance, which is actually, there's an error in the, in the error. So stupid. And there's an error in the mean, there's an error in everything that you do because basically there's always uncertainties related to things. Yeah,
so then basically you could say like there's a 10% chance that it is actually true that I walked 5.
Which is why.
If it's like on the edge.
You're right. Which is where the difference comes between two fundamental concepts in statistics. Confidence intervals and prediction intervals. So confidence intervals, I mean, if you've done, I don't know, what was this? Was this in high school? I think so. No, didn't do it. No, we didn't do it. Okay, definitely in a statistics class though, because I definitely remember, I think, doing. So if you've taken a statistics class or are interested in statistics, you may be knowledgeable of confidence intervals. You're basically saying how confident am I that this thing of this distribution is that. When I say this thing and that, I'm basically saying like a property of the distribution is something. For example, what is the chance that the mean is 5? That's basically what I'm saying. The mean is the this, the 5 is the that, right? So, wait, I lost my train of thought. Remind me where I was?
Confidence intervals.
Thank you so much. So in this confidence interval, basically what I'm doing is usually you have a cutoff. You have a 95% confidence interval, a 97% confidence interval, all of those things.
100%.
So basically what you're doing in those confidence intervals is you're just cutting off the sides of your standardized variable. You're standardizing it and you're saying, okay, let's just take the 95%. And what are the values at the 95% confidence or at like once I've cut off the tail.
In this case, it would just be 2.5 on each side.
Like right? whatever it would be in this case, because it would be simple. But I'm saying in any situation, all you would have to do is in the confidence interval, you would have to, apply this hypothesis test. And you would say, hey, how confident am I that this predictor is in this interval? and you are 95% confident. So you're not even 100% confident that it's in there.
Yeah, but 95% of the time it will
But
be.
then no. Yeah, 95%. Yeah, very correct interpretation. That's always misled. 95% of the time it will be in there. You're correct. But here's the crazy thing.
Wait, isn't that the wrong
No.
interpretation?
95% of the time is the confidence interval interpretation. And then comes the prediction interval, which is 100% of the time. It is found here with no. Wait, I'm mixing it up. One second. Confidence
That's confidence interval.
No. That's not confidence intervals. I know that. Because confidence is like, I'm 95% confident that the predicted value is in the range. And prediction is like, because you can still have like 95% prediction intervals, right? So in confidence intervals, it's like 95% of the time it'll be here. But in prediction intervals, it will definitely be in the interval. Then what's the 95% for though? I'm forgetting the exact thing here, man. I'm so sorry. Like I wish I could kind of streamline this a little more correctly. But basically the point that onto what you were making is that the prediction interval factors in extra variation. So you actually add 1. You just add 1 when you're calculating your hypothesis test. You just add 1. Because you're basically counting for an extra probability that you might be wrong with your confidence test. So there's a lot of uncertainties. There's a lot of errors. There's a lot of ways of approaching and interpreting this, any real statistical data, which is where all these different interpretations come from. Which is why statistics can be so misleading sometimes. You can be like, 60% of Americans said this, surveyed from 10,000 people. What? There's so many times where you have to really read the fine print to understand where their interpretation came from.
Yeah.
Right. A big part of this is also using like these small samples to approximate things for the population. Like that's also kind of like another fundamental statement of probability, of statistics, really. Not probability. You are taking in a sample of data because you never really have all the population, right? You're taking a sample.
I mean, you could if it was like all of America, you can get the whole.
But hardly, because like, what if the guy's born 2 seconds after you just did it?
Just ask him.
I'm just saying, like if you take like the mean heights of everyone in the world, you're not gonna get 7 billion heights.
Maybe
you doubtful.
You could.
Like when people say the average the population of the world, and when people say what's the average height of the world, they don't actually calculate it. They don't ask you, hey, what's your height? No,
I've never been asked.
No, that's what I'm saying. It's not like someone actually asks you. It's done on a sample and it's approximated for the population, and that is statistics.
Wait, that's kind of messed up because I feel like we would both increase the world average, right?
I mean, but then the same 2 people would decrease it probably to somewhere else.
I guess, but so are you saying it is?
No, but that's the whole point, right?
No,
you're taking a small sample, and obviously the bigger your sample, the more representative of the population that you get. That's why it's so important when you actually apply statistics to take the correct sample. When I say correct, I mean it needs to be random, right? There needs to be no bias. So it's not like, for example, it can't be a survey where you have the choice to give it back. Because then some people that just don't fit into it will just say no and just not return it. So there can be no bias in that way. It needs to be randomly generated. It's not only from like one town, for example. And that's basically the idea of a representative sample. When you have a representative sample, analysis on said sample can give you some inference on what the population can be. It's not going to actually tell you the average is exactly this, of course, but it's going to give you a confidence interval. Right? It's going to give you a prediction interval. It's going to be like, hey, in 10 years, the average is going to be this. I mean, I don't know if we're really doing it against time, but I'm just saying, like, you can do all sorts of things with these intervals because of the power of, just hypothesis testing and just using them as, these models, modeling the data. Super cool.
I wanted to talk about spin.
Yeah, I know.
But I don't think that is going to happen.
I thought it would be a bounce off kind of thing. We did a little bouncing off, but not an opposite in the same.
I think
topic.
you spoke a lot longer than I did because
I doubt it.
Because the intro was like 5-6 minutes, and I spoke till 30 minutes.
Okay, man. I spoke a little longer than you. I'm sorry.
Anyways.
You want to talk?
No, it's all good. I mean, I could actually. We'll do a little bit on spin. a little bit just to end the conversation.
Sure, we can talk about some spin
on something truly interesting.
Oh wow! Yeah, I'm talking about real data here, okay, man. I'm talking about observation.
Here is something that will blow your mind. Imagine you're in the 1700s, right? What do you really know? Think about that. Did you know that there is a quantity that exists that can be measured and just people don't know about it? Guess what? That quantity is called spin. How do we know it exists? Well, first of all, this actually was first discovered by Stern and Gerlach in the famous Stern-Gerlach experiment, where what they did is they have this magnetic field and they send silver atoms through that magnetic field, and they get these atoms from like this furnace, and then it creates a beam of atoms that passes through. And they know like the angular momentum of the atom can change, and what they expected was that, well, depending on the magnetic moment of the atom, and they know what the magnetic field is that's applied to, or that the atoms go through. They know what it is already, and so they're like, okay, since we think that these moments related to the angular momentum of the electrons, the reason why they chose silver is because it has one valence electron. And so, they did a little bit of math. They're like, yeah, it should come out as like this like weird flat normal distribution of the atoms, getting deflected by the magnetic field. But contrary to popular belief at the time, they actually found that, well, when you measure the angular momentum of the atom, you find that it either goes up or it either goes down. And so they're like, hold up. How is it possible that this vector can point in any direction? And when you send it through the magnetic field, it's essentially like a dot product, right? You see like how far in the, let's say the magnetic field points upwards. It's like how much of a component is there upwards, and if it's negative, then it'll go down. If it's a positive component, then it'll go up. They're like, why is it that every single atom we send through, it either goes just up or goes just down? It actually turns out that there is something called spin that people didn't know about, and that is a legitimate thing that you can observe. And the thing that really sucks is that I wanted to connect this discussion to observables, because I was talking about observables earlier. And the thing about spin is that it is quantized. And this is an example of an observable that is not represented by an infinite dimensional matrix. It's actually represented by a 2x2 matrix. Yes. And so, well, depending on, how many directions you're looking at.
I was just going to say, like, 2x2 is always just for special. If we
have it's always 2x2 if you're just looking at the spin along one direction.
Exactly. That's what I'm saying. So if you're looking Y and Z and X.
Exactly. But this is just going to be like a tensor product, right? Because observing along one, or actually, that's not even true. Forget what I just said. So I wanted to talk about spin because the spin operators don't commute either. And I wanted to talk a little bit about that and how you can kind of get this little, it's not really an analogy, but when you look at the position and momentum operators that you can operate, don't do that, that you can operate on a state. Sorry, Ray was rubbing his face on the mic.
What? No, I was just talking.
I could hear it. Anyways, okay. What was I saying? Something about spin. Operating. Yeah, so they don't commute, which means that when you this has so many beautiful connections with like polarization and all this stuff. But when you observe the spin, basically it collapses the state of the thing into the, in this case, there's only two possible choices, and it's spin up or spin down. Of course, we're talking about only spin half systems. So when you observe the spin of something, you're either going to get spin up, spin down. And once you measure that thing, it is now in the state of either up or down. And one thing, I guess I should maybe explain this in another episode, but these spin directions are orthogonal to each other, which means that if you measure the spin to be in one direction, then you have no idea which way it's going to collapse into in the other spin directions, as long as they're orthogonal to each other. You can also define a general spin direction, which is usually, like the spin operator is usually a capital S and then subscript whichever direction you're looking in. And the general spin operator is like Sn, and n is like some unit vector pointing in some direction, or Su or whatever. And then, depending on the angle that the two axes make, you will get different probabilities to be in each state after measuring it, because you can kind of imagine this as a projection, right? If you have an X and Y axis, then what you're basically doing when you measure the spin of something, let's say you measure in the X direction, you're projecting it onto the X axis. And then when you project it then onto the Y axis, there's no component in either direction on the Y axis. And so if you ask the question, like, what state is it more likely to be in? Well, it's exactly on the X axis. So you have no clue. Mm-hmm. But when you measure it, remember, zero is not an option. Like spin, you can't measure zero spin. You know, in a spin half system, you can't measure zero spin, which means it either has to have up or down. And so this is an exact, like an exact way to be like, this is so bad the way I said it, but this is a perfect representation of like a 50-50 probability. Mm-hmm. And same thing goes with polarization. Listen to our first episode on quantum mechanics, or the second episode, I don't remember. But we do talk about polarization, and you will definitely appreciate that. When
I think we briefly spoke about Schrodinger Equation there too. I think that was
right.
Probably. Yeah, I think that was good
for sure. Anyways,
yeah, spin is always like misled to always. Some people think of it as like the actual thing spinning.
No.
Yeah, that's always like a terrible way to think about it.
Yep.
Because like spin half, like I know the first time I read it in a book or something, it's like if you draw a dot on a ball, you spin it once. You don't see the dot, like one whole 360. You see it, you spin it another 360 times, you then see the dot. What the hell? What does that mean?
Yeah.
Like, that's just not, like, zero intuition at all. What kind of ball follows that property? Like, that's just the worst. So like the word spin, don't think is the best way to think about it. But, because I think that actually really makes you, really misleads you into thinking about spin. Because for a long time, I was thinking about it like that. But then, when there are multiple directions of spin, and I'm like, wait, this just makes no sense anymore. So yeah, better way to think about it, like a little more quantum mechanically, and it's like different states and stuff like that, but just a different way to think about it.
Well, that concludes the episode.
We just spoke about, I think that was we kind of did half there, which was not intended, but whatever, we did it.
So yeah, if you enjoyed listening to this episode, make sure to follow us wherever you're listening. Make sure to like the YouTube video and do all of that stuff. Other than that, thank you for listening. This has been episode number 88 of the Math and Physics Podcast, and I'm your host, Parker.
And I'm Ray. We'll see you soon.
Bye, guys.